We've been lecturing on chapter 10, which is about energy. And we talked about some stuff last time, whatever that stuff was. But we talked really about a couple of major things, which was delta H, again, which is our enthalpy. And again, that's really our heat of reaction, as we've been talking about. The actual sort of sign that you end up with in terms of delta H, if it's negative, again, that's going to be an exothermic reaction. If it is a positive, it is going to be endothermic. And one way that we can calculate delta H is to really go our sort of final minus initial, which is our products minus our reactants. So we could calculate the delta H for the reaction by taking the delta H of all of our products and subtract it from the delta H of all of our reactants. And remember that this is typically sort of table values where you would go look these guys up. So you look up the enthalpy values, and they're sometimes referred to in the table or just in general as delta H of F, or formation. And those are sort of the values that you would look up in the table. Remember that if you have to go look it up in a table, you not only want to find obviously the substance you're looking for, but you also want to make sure it's the correct phase of it. So if it's a liquid, a solid, a gas, whatever it may be. As we saw in a couple of the examples we did, most things that are sort of in their elemental form, their sort of standard form, really not combined with anything else, just like an element by itself, or like H2O2 diatomic molecule, if it's some of those guys, they typically will have values of 0. So there are some that do have values of 0. We basically add up all the products and reactants. The other major thing that you want to do when you do that calculation is, again, you do not want to ignore the coefficients. So, we would take the coefficients for each of them that we look up, multiply the value that we get in the table, and we want to do that for everybody that is there. We finished up last time starting to talk about specific heat. And specific heat has an equation, Q is equal to ms delta T, Q being heat, which again has units of joules or calories. M is the mass, which has units of grams. S is the specific heat capacity. Which has units, bless you, of joules per gram per degree Celsius, or calories per gram per degree Celsius. And our delta T is always, we want to do our final minus our initial, and that can be in degrees Celsius, and that is because our specific heat capacity is usually in degrees Celsius, so we can leave it like that. Remember that, as we talked about last time, it really is sort of this sort of calculation there that will determine whether or not you'll end up with really a negative or a positive value for Q. And remember that if you do end up with a negative value for Q, much like delta H, that would mean it's an exothermic process, heat and energy is released. If you end up with a positive value for Q, then it is an endothermic process and energy is absorbed. An important number that you should know is the specific heat capacity of liquid water. Comes up a lot, 4.184 joules per gram per degree Celsius, or 1 calorie per gram per degree Celsius. That again is, as we also talked about, really the conversion factor to go between calories and joules, 4.184 joules in a calorie. So if you remember the specific heat capacity for liquid water, you also know the conversion factor to go from joules to calories. Any questions on any of that there that we talked about? Okay, so we did an example last time. Let's do another one here. I think this is where we left off. So take a moment or two here, and if we have 294 joules of heat is transferred to a 10-gram sample of silver at 25 degrees, what will be the final temperature of the silver? Specific heat capacity of silver, 0.24 joules per gram per degree Celsius. So take a couple moments here and see what you come up with. Okay, let's take a look. So obviously we're dealing with specific heat, so we want to use our Q is equal to ms delta T. In this case, we are given the heat, so that is Q. We're given the mass here, which is 10 grams. We do have the initial temperature given to us, 25. And in here, we are looking for the final temperature. So we really have everything here except for really the change in temperature part. So we could just plug it in. And we got 294 joules is equal to our 10 grams times our 0.24 joules per gram per degree Celsius. And if you want, you can leave as a delta T, or you could do obviously final minus initial in that case. At this point, we're basically going to divide everybody to the other side. And when we do that, we'll get 294 divided by 10 and divided by 0.24. Going to give us 122.5 unit wise. The joules here will cancel as we divide. So will the grams. This would now be degrees Celsius equals our change in temperature, which is our final minus our initial temperature, right? So in this case, it's important to make sure it is final minus initial. So when we do that, we got a 122.5 is equal to our final temperature minus 25 degrees Celsius, which was our initial. That means we're going to add that to both sides. Those will cancel, and that will get us something like a final temperature of 147.5 degrees Celsius. Significant figure wise, here we're dividing first off. So that is 3 sig figs, 3 sig figs, 2 sig figs. Means really this guy should have ended up at 2 sig figs, and then we're adding. So really there's no decimal point. This should be in either of those numbers. So we should end up at like a whole number, 148 degrees Celsius. Now, if you went to the right sig figs on that point, I think you end up with like 145. If you kind of rounded earlier on, either one would be okay. Yes. Any questions on that particular one there? It does make sense. Yeah. I added 25 because what we solved for was the change in temperature, right? And the change in temperature is always final minus initial. And that means that essentially what we had here was 122.5 degrees Celsius equals our final minus 25 degrees Celsius, as that was our initial. So to bring it to the other side, we got to do the opposite, and we got to add it, right? And in this case, it does make sense, and it can be done incorrectly. Maybe if you did subtract, in this case, it absorbed 294 joules of energy, which is positive, right? Endothermic, which we would expect the final temperature then to be higher, right? Because it absorbed the energy. So if you accidentally subtracted here and you ended up with a lower temperature, it really wouldn't make sense based on the 294 value there. That's positive because you should be absorbing energy, which should result in temperature going up in that case. And that's why you always want to do final minus initial so that you add when you should or subtract when you should. Yeah. No, it's so if we just follow sort of the sig figs as we did the calculation, really up here in this range where we divided basically, right? We had 3 sig figs for this guy, 3 sig figs for this one, and 2 sig figs, which means technically speaking, when we got the answer on the left-hand side here, it actually should have went to 2 sig figs right about there. Which means technically if you did round at that point, you would have rounded to like 120, no decimal. And that's important because technically down here, if you did the rounding, which I didn't, I obviously kept the number and kept going. But if you did the rounding, the last thing we did was adding, and that would technically leave that 120 with no decimal places, right? And the 25 would have no decimal places, which is why we should end up really with an answer that has no decimal places in this case. But it does have 3 significant figures, but it's really actually no decimal places since the adding was the last thing that we did. Yeah. And like I said, if you did round to 120, you would end up with like a 145 at the end, and that would be okay as well. Yeah. Other questions? So again, we kind of did multiple calculations here. You want to sort of keep track of it. And again, if you don't want to round to the very end, then that's all good. But if you do round, You know, that's technically how we get to really no decimal places here on the last one. Other questions? Okay. All right, so next thing we're going to talk about is a process where there's like a transfer of energy. So when heat is transferred from one object to the next, the amount of energy that is lost by one object is the exact same amount of energy that's gained by another. So as we talked about, sort of this perfect transfer of energy from one place to the next. So very commonly, this occurs, and it's going to occur today in lab when we do the experiment. But for example, if I had, say, a beaker of water, and let's just say it was at an initial temperature, say, of 32 degrees, a little warm. And I had a piece of metal here. And let's say initially we heat this metal up to like 95 degrees Celsius. And let's just say the mass of the metal was 100 grams. And when I go, and we'll say here we have a mass of water of like 75 grams, something like that. So when I go throw this hot piece of metal into, or in this case, what's going to happen with the temperature of the metal? Will it go up or will it go down? It will go down because the water is cooler, right? And the metal is hotter. Heat flows from hot to cold. So what's going to happen, right, is the hot piece of metal will release the energy, right, to the water that it's sitting in. That's going to heat up the water, right? And that's also going to cool down the metal. So let's just say that the water heats up afterwards, after you do that, to like 38 degrees Celsius. Now, when you do this, the final temperature of the metal will end up being what temperature? It'll be exactly the same as the water, right? Because it's basically sitting up there, so it's going to come to equilibrium, right, with the temperature of the water. So the final temperature of the metal here would also be 38 degrees Celsius. So if we wanted to know something like the specific heat capacity of the metal, we could actually use water to help us sort of calculate that. So when we do this, there's really kind of two pieces of information here. There is the metal and basically the water. And if we look at the metal, we know the mass of the metal in my made up example here is 100 grams. We know that the initial temperature is 95 degrees Celsius. We know the final temperature will equal that of the water we threw it in. And we're looking for the specific heat capacity. We also don't know Q at this point for the metal. For the water, we do know, obviously, the mass of it was 75 degrees in this case. We do know that the initial temperature of the water is 32 degrees Celsius. We know the final temperature of the water is 38 degrees Celsius. We do know the specific heat of liquid water. That is our 4.184 number. So we always know that, right? And that means that we have enough information, if we look at the water, to actually calculate the heat, in this case, that the water is going to absorb as the hot piece of metal goes into it. So if we start with that, Q of the water will equal ms delta T, putting in our numbers here. We have 75 grams in my made up example here. We have our specific heat capacity of the liquid water. Once again, we want to do final minus initial here for the temperature. So final being 32 degrees Celsius minus initial 20, not 25, what did I do there? 38 degrees. 38 degrees Celsius minus 32 degrees Celsius. There we go. And if we do all that there, we end up with 75 times 4.184 times 38 minus 32, which gives us something in this example of 1882.8 joules. Again, the grams will cancel, degrees Celsius will cancel. here. Now this is, sure I punched that in correctly here. I did. So this gives us the amount of energy that was absorbed by the water. It is a positive number. And if we look at sig figs here, by the way, this is going to give us 2 sig figs, right? When we subtract it, this will have 4 sig figs and this will have 3, which means technically this should end up at something like 1900 joules of energy, right? When we do it. So this is 1900 joules of energy. It is a positive number, which means for the water, exothermic or endothermic. The water, it is endothermic, right? It's picking up all that heat and energy from the hot piece of metal. So it's endothermic. Now, 100% of all that energy that the water picked up came from the metal, right? So what this tells us is the amount of energy that the water picks up will be equal to negative the amount of energy that the metal released. So by doing this calculation, we know that really the metal here released negative 1900 joules of energy. If we take the rounded number, yeah. You can. Again, probably at this point, you may want to round because you're going to take that number to the next step. But if you don't necessarily have to. You could do it at the end. You should, again, kind of clean it up to the right number of digits. So you want to kind of keep track of it. So if you don't want to, you could just kind of mark, should kind of be in that area so that once you finish up doing the next calculation, you kind of know where to end. It'll be okay either way. Yeah, that's good. Other questions? So what that means is we now have enough information. If we look at Q of the metal will equal ms delta T. If we want to solve for S of the metal, we're going to divide both of these guys to the other side, and that will give us Q of the metal divided by M and delta T. So putting in our numbers, and again, if you want to use a round number, you can. If you, again, just want to kind of carry over the original number on your calculator, you can do that as well. But it does need to be negative here. And we're going to divide it by our mass of the metal, which was 100 grams. Now, also important here, the final temperature of our metal is, in this example, 38 degrees. Minus our final temperature, our initial temperature, which was 95 degrees Celsius. Why is this calculation important to do it that way? What kind of number are you going to get when you do it? You can get a negative number, and that negative is important because this negative and that negative on the bottom will turn your specific heat capacity back to a positive number, which is what it should be. So again, that's what you would do there. So if we pick that number and we divide it by 100, and we also divided it by our 38 minus 95, we end up with 0.33. Now, again, this is why it's important to recognize where we should end here, right? Because now, technically speaking, that's 2 sig figs up on top. That's the 4 sig figs. And when we subtract this, you have about 3 sig figs, I think, which means our answer should end up at 2. So again, it's important to keep track of that and carry it along so you understand at the end what it should end up being. Now, in terms of units, none of these units cancel. So you end up with joules per gram per degree Celsius. So all those units end, and those are the proper units for specific heat capacity. So this is a very common way, and exactly what we're going to do in lab today, that you could use really water and basically a thermometer and keep track of the change in temperature that occurs with the water. That allows you to keep track of basically how much energy the water is gaining, and by default, how much energy something else is losing. Any questions on that? You could do this all in one calculation with the formula on the next page. You just got to make one side negative. Sometimes it's easier to split it up and just kind of do 2 separate calculations so you don't get the negative sign. Sometimes when people try to use sort of this equation we just saw there, You got to move really one of these guys all the way over to the other side, which changes it to negative. Sometimes people will add when they should subtract when they should add. So sometimes it's easier just kind of separate and do two separate calculations, one for the water and then one for the metal or whatever piece of stuff that you're looking at. Any questions on that there? All right, so why don't you try one here then? We have 110 grams sample of metal. It at 55 degrees Celsius raises the temperature 150 milliliters of water from 23 degrees to 25.5. What is the specific heat capacity of the metal? Okay, let's take a look. So again, it's basically the same situation. We got a kind of beaker of water, and we're going to throw sort of a hot piece of metal. So we do have two things here. We have our metal, and in terms of our metal and our water, for our metal, we do have the mass is 110 grams. We do have it initial temperature of 55.5. We have 150 milliliters of water, which if you take 150 milliliters and you times it by 1 gram per milliliter, you will end up with 150 grams of water. So we have the mass of it as 150 grams. The initial temperature of the water is 23 degrees Celsius. The final temperature of the water is 25.5 degrees Celsius. Remember, as we just talked about, that also will then be the final temperature of the metal as it's sitting in that water. So we do know the final temperature of our metal there will be 25.5 degrees Celsius. We also do know the specific heat capacity there of water, which is 4.184 joules per gram per degree Celsius. That is what we are looking for here. So once again, here we have pretty much like normal, all the information for water. So that is where we're going to start. So the Q of water will equal our mass, which is 150 grams, times the specific heat capacity. Again, doing final temperature minus initial temperature for our water will give us here 150 times 4.184 times 25.5 minus 23. Going to give us, I think, 1569, if I'm not mistaken there. The units here would be joules, as again, the grams would cancel, degrees Celsius will cancel, and we would end up with joules. Now, again, if we want to kind of keep track of our sig figs, we should end up with how many sig figs in this one? This has 4. This has 4, and this one, when we subtract, I believe is 2.5, which is 2, which means technically speaking, that is where, you know, it should end. I again going to keep the whole number here and just kind of clean it up at the end like we did on the last one. We now know that that amount of energy that was gained by the water had to come from the metal. So using that relationship, that basically Q of the water equals minus Q of the metal. We now know that Q of the metal should be negative 1569. Again, here, water's temperature went up, metal's temperature went down, which means it's exothermic for the metal, endothermic for the water. And now we have everything that we need for the metal. So our Q of our metal will equal MS delta T. Once again, dividing these guys to the other side gives us the specific heat of the metal will equal our Q, M, and delta T. Our Q here again being negative 1569 joules divided by the mass of the metal, 110. And again, final minus initial. So that's going to give us our 25.5 minus our 55.5 degrees Celsius. And once again, that's going to give us the negative number that we need to get rid of the negative number up on top. And that's going to divide out our 110 divided by 25.5 minus 55.5 gets us 0. We'll call it 48 joules per gram per degree Celsius, as none of those units cancel. Now, sig fig wise, why we kept track above. Once again, we should have ended here, which would be 2 sig figs, 4 sig figs, and when we subtract here, we have somewhere like 3 sig figs, so we should end up with 2 at the end of it. Question on that there? Yeah.
Next, for S on
So that's a value that you should know. So the specific heat of water is always, for liquid water, it does change if it's ice or steam, but for liquid water, specific heat capacity is always 4.184 joules per gram per degree Celsius, or it is 1 calorie per gram per degree Celsius. So those are 2 different versions of it. But that's sort of a known value that you kind of always have if it's liquid water.
Okay.
You should, yeah. So we use it a lot, and we'll use it a lot today in the lab. But that's the number they expect you to kind of know. It does change, like I said. I think we saw the table the other day. Again, bless you, ice and like steam, they're like 2.03 and 2, so they're a little bit different. But definitely most of the time we'll do an experiment. I would involve liquid water, so that 4.184 comes up a lot.
1, 5, 6.
Yeah. Yeah, so the idea here is, for example, basically the piece of metal is hotter than the liquid water. So when it goes for a swim, it's going to release basically all that energy to the water. So when we calculate the Q for the water, we end up with a positive number, which makes sense because it's gaining all that energy from the metal that's in there. And that means that it's endothermic for the water, right? It's picking up all that energy. The opposite of that, all that energy had to come from the piece of metal. So for the metal, it's actually exothermic, which would be a negative value. The value would be exactly the same, just the sign would change. Is that kind of perfect transfer of energy we've been talking about, that, you know, somebody loses a certain amount of energy, somebody else has to gain the exact same amount. The only way we kind of represent the difference is with the sign. So one is losing the energy or giving it up, and that's sort of exothermic, and that's negative sign. And then the other one's positive, as is gaining it. So that's why that 1569, all that energy had to come from the metal. So it's the exact same number for the metal, just negative because it's exothermic. Other questions? All right. So in this case, obviously the water temperature went up, right? We could have the water temperature go down, right? If we throw something that came out of the freezer right into it, right? It would be the same calculation, except if I put a really cold piece of metal into water, in this case, the water is hotter, right? The cold piece of metal is colder. So it's actually going to be the water losing the energy, right? And the metal will actually gain the energy. So it works the same way. One will be exothermic and one will be endothermic. Question on specific heat. Okay. So we talked a little bit about energy and nutrition. I think we talked about it earlier, but remember that when we talk about calories that have a capital C, that is nutritional calories. And once again, one of the capital calories is actually 1,000 of the little calories, which is also 1 kilocalorie. It's also sometimes referred to as a nutritional calorie. A calorimeter is an apparatus that's used to determine the number of calories in food. It's basically a device, as we'll see a little picture of it, where you basically kind of set it on fire, and as it burns, basically the water temperature changes. So you can figure out how much energy came off from the piece of food and figure out how many calories that piece of food is. So let's take a look at one of those there. So there's like, we'll just go with our cookie here. There's some oxygen. You make a spark, the cookie catches on fire. This is all a nice insulated container, thermometer. So as this sort of cookie or whatever starts to burn, it's going to give off heat and energy to the water that's surrounding it. It's going to cause a change in temperature. And through a very simple calculation like we just did, you can basically figure out how much energy was gained by the water. that would be how much energy was lost by the piece of food. And you could change it into nutritional calories, and you'll know how much calories there are per how much you burnt or whatever it may be, or set up on fire. It's how they get the calorie count on the back of your food and stuff like that. Yeah, they do something similar to this where that's basically how you do it. Years ago in labs, we used to do kind of things like that. You bring like a Cheeto and like all you need is like a Coke can with some water, put the Cheeto underneath and set it on fire, take the temperature change in the Coke can of the water, and you could figure out how much, calories coming off your Cheeto or whatever it may be in that particular case. But yeah, they do something like that to get those nutritional calories. They also, if they don't kind of do something like that, which they probably do, they also could do sort of a caloric calculation. And the major food types do have sort of caloric values for carbohydrates, fats, and proteins. Carbohydrates and proteins are actually 4 kilocalories per gram each. Remember, a kilocalorie is really a nutritional calorie, and fat is like 9 kilocalories per gram. So a lot of times this is how they could also kind of figure out what's on the nutritional label. The values are on the nutritional label based on how much carbohydrates they put in there, how many grams of fats they put on it, or stuff like that. If you look at a label, you will also sometimes see those values given to you. You'll see how many grams of carbs there are, how many grams of fat, how many grams of protein there are. Anybody got like a candy bar or anything like that? A chip, say that? It's got nutrition? No? Okay. Well, when you look at them, you'll be able to actually see it. And again, you can multiply each of those things by that. And that's how they typically will get the calories. Yeah. Yes, everything we're talking about is still exams here. Yeah. So if you look at those labels, you'll see it. And if you ever do the calculation on the labels, typically speaking, they kind of usually round down for the overall calories. I'm not sure why they would do that, but they usually will round down like that. So constant pressure calorimetry is another sort of way that you could kind of do this. And this is basically what we're going to be doing today. You really do this sort of process with nothing more than a couple of coffee cups and some water and a thermometer. And it's all you need really to figure out how much energy is being given off and stuff like that. So very much like what we'll use today, a couple of styrofoam cups. You can put your reaction in there, thermometer through the top, put a lid on it. And again, by following really the change in the temperature of the solution or water, a lot of reactions happen with aqueous solutions. And that's basically like a water environment. So even if you were not doing like, a piece of metal and water or something like that, but you mix a couple of chemicals together that created a chemical reaction, because they're probably mostly based aqueous and mostly water, you can use the specific heat capacity of water and it will work the exact same way. When you do something like this at constant pressure, which is essentially what we do in lab, when you do calculate Q through that calculation, it is sort of the same value that would be for the enthalpy change in that particular reaction. So at constant pressure, they will equal each other. And it's a super simple way to really figure out, how much energy is being released when you do any type of reaction. Again, all you need is really that thermometer to carry through. So for example, in terms of the nutritional calories, if we had something like this, just to look at it, the calculation here. So if we had 1 ounce of oat bran, to have a cup of milk, 22 grams of carbs in that, 7 grams of fat, and 10 grams of protein. If you eat 2 servings, how many calories would you have? So again, we take our mass of carbohydrates times the caloric value, the grams cancel. Our grams of fat times the caloric value for fat, and the caloric value there for protein. These are all basically calories here, nutritional calories. And when you add them together, you get something like 191 kilocalories per serving. And if you obviously ate 2 of them, you times it by 2. And that means that you had about 382 kilocalories or 382 nutritional calories, which is the same thing. So again, on pretty much all nutrition labels, there will be those three categories listed and how many grams of each of them. And when you do it, it should come up to the calories that they show per serving. Any questions on that calculation there? Okay, so the next thing we're going to talk about is enthalpy, and another way that we can sort of calculate the change in enthalpy for a reaction. So earlier on, we talked about sort of calculating it, obviously using products minus reactants. There are some cases where we actually can use a number of different individual reactions to figure out what's going on overall in a energy for the whole entire reaction. So let's talk a little bit about thermochemical equations. And those are really just equations where we also have the delta H value given to us. So in this case, this is going from solid water to liquid water. The delta H for this reaction is 6.01 kilojoules. So when we go from ice to liquid water, we need to put energy in or take energy out. Energy needs to go in to do that, right? And it's endothermic, and that is why this value here is positive. Now, if I wanted to do the opposite move, basically take liquid water and make it back to ice, energy needs to be released in that case, which means it's exothermic. And what happens is if we reverse the reaction, so that is the reverse of this reaction, we now have the exact same number, except that it is negative and exothermic, which is what has to happen when you go from liquid water to solid ice. So if you have a reaction that has a delta H value and you need to reverse it, and we'll talk why you might need to do that in just a second, but in some cases you may not need it the way it's written. You may need really the reverse reaction. What happens to the delta H value is you simply change the sign. So if it was positive, it becomes negative. If it was negative, it will become positive. So if you ever need to take a reaction and reverse it, the delta H sign also gets changed. Now, sometimes what happens if we were not just needing, say, 1 mole of water, but we needed 2 moles of it? So the difference between the top equation here and the bottom equation is we multiplied everybody by 2, basically multiplied by 2. And how that affects the delta H value is if you multiply by a common number, you then would multiply the delta H value by that number. And for that reaction, it then would require 12 kilojoules of energy. So another very common thing that you need to do with equations is multiply the equation by a common number. How that affects the delta H value is you multiply the delta H value by that number as well. The last thing that you could do is divide by a common number. So if we went from the bottom equation back to the top equation, and I divided everybody here by 2, what I would end up doing is ending up with water like the top equation. And I would be back to my 6.01 kilojoules. So if you have to divide an equation by a common number, the delta H value gets divided. So those are really kind of the 3 things that you could do to an equation and how it will affect the actual delta H value for the equation you're looking at. Once again, if you reverse the reaction, you change the sign of the delta H. So either it goes from positive to negative or negative to positive. If you multiply by a common number, you should multiply the delta H by the same number. And if you divide by a common number, you should divide the delta H by a common number. Any questions on that there? So why is this important? This is important because there's a process which is known as Hess's Law. And the idea behind Hess's Law is this: not all reactions take place in a one-step fashion. So for example, if you had A plus B goes to E plus F, this may not happen in like just one reaction. It may actually happen in multiple reactions. So maybe the first thing that happens is like A plus B makes C plus D. Then C plus D makes E plus F. And there may be a delta H value for each of these steps. So when we add these equations together, and whenever you add equations together, anything on opposite sides of the arrow will cancel or reduce down. So there's C on the left-hand side, C on the right-hand side. They cancel each other. It's like subtracting it to the other side. They cancel. D's on the left-hand side, D's on the right-hand side, so they cancel. Once you get rid of everything that cancels or reduces down, everybody on the left stays on the left, everybody on the right-hand side of the arrow stays on the right-hand side of the arrow, and that leaves us A plus B goes to E plus F. We'll call that 1 and 2. Any questions on that? Now, when you do something like this, to get the delta H for this reaction at the bottom, we just add the two delta H's together. So delta H here would equal our delta H1 plus our delta H2. So we add both of those together, and that will give us the overall energy for that reaction. So for example, here, if we look at the bottom, when we add this together, the waters cancel, and that leaves us H2 on the left, half of O2 on the left, and H2O on the right. The difference between those water is one's in the gas state and one's in the liquid state. So that's why they didn't all cancel. When we do that, we would then add these two numbers together to get our negative 285.8 kilojoules of energy. Now, for example, let's say that we needed the top reaction, not the way it was written, but I needed it like this, which is basically the reverse of it. What would the delta H value for that reaction be? It would be the exact same number as this, but because we reversed it, it just becomes a positive number, and it would be positive 241.8 kilojoules, right? Now, once again, let's say if we needed this reaction, but we needed two of them, and we had to multiply that bottom reaction by 2, we would multiply both of the guys in the reaction by 2, and then to this value, I should do what? Should also multiply it by 2. So the delta H for this one would be negative 88 kilojoules. So again, if you need to do some type of manipulation to those equations, you need to keep track of what you do. So really what Hess's law is kind of like a puzzle problem, if you will. You will have a number of different individual equations that you may have to reverse, you may have to multiply by a number, you may have to divide by a number, you may not have to do anything to it, but you need to arrange all the individual equations in such a way that when you go add them together, everything cancels out and you're left with the equation you're looking for. And then you just add up all the delta H's and keep track of what you did to it. So let's take a look at one here, I think. So for example, here, what we want to do is end up with this equation, and we want to know what is the delta H value for that particular equation. We're going to use these two equations here to basically build it. The best way to do it is to really just keep it simple. It's like, okay, is it on the left-hand side of the arrow or the right-hand side of the arrow, and how much do I need? So what I mean by that in this particular example, I would look at the carbon perhaps first. And really the only equation that has carbon in it is the top one, and it's on the left-hand side, and that's exactly where I need it, right? And in the final equation, I just need one of the carbons, and that's what I have in this particular equation. So in this case, I'm really not going to do anything to this equation. I'm just going to keep it the way it is. And because I did not do anything to this equation, that means my delta H value will remain the same. Right, we're not going to change it because we didn't do anything to it. The next thing you might want to look at is like CO2. I see the CO2 is on the right-hand side of the arrow. The only one that has CO2 on the right-hand side of the arrow there is the bottom, and it's on the correct side. So once again, in this case, I do not need to do anything to it. So we will end up with CO plus 1/2, bless you, goes to CO2. And once again, because I didn't change the equation, I'm going to actually leave it the way it is. Now, if I did this correctly, when I add these equations together, I should end up with the equation I'm looking for. So in this case, the CO on the left and the CO on the right will cancel each other out. And that's everything that will cancel. That will leave me a carbon plus a half of O2, and a half of O2 gives me 1 O2, right? When you add that together, and gives me CO2. And in this case, to get the delta H of this, we're just going to simply add those two values together, minus 110 plus minus 283 kilojoules, going to give us here 110 plus 283. There you go. Negative 393 kilojoules in this case. So in this case, we actually did not need to actually change any of the equations. Sometimes that happens. A lot of times you do need to change some of the equations. Overall, this reaction would be exothermic or endothermic here. This would be exothermic. We have a negative value. Yeah. 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 So anything on opposite sides of the arrow can either fully cancel or just reduce down. It's kind of like you're subtracting. You think of the arrow like an equal sign. So you're going to bring basically the CO to the other side and subtract it from the CO that was there. So you have like a positive CO and a negative CO. So kind of like 2 minus 2 to the other side. It'll basically cancel each other out. Yeah. Other questions? And again, they may not always completely cancel out, but you can sometimes just reduce something down. You know, if you had 4 on one side and 3 on the other, you could take the 3 to the other side and just be left with 1. So it doesn't necessarily always have to completely cancel. All right, so that was a pretty straightforward one. Let's try another one here and see what you get. All right, so we're looking for the delta H value for this reaction, and you want to make it based on this top reaction here. And I anticipate you might have to do some rearranging of those top ones. So take a moment or two, rearrange them, keep track of what you did so you can adjust the delta H value correctly. Usually good for these sort of Hess's law type of situations. Simply, I'm just going to look in my desired equation. I see N2 on the left-hand side. I do see my N2 in this equation, and it is on the left-hand side, so that's all good. But I do need to end up with 2 of them, and here I have a half. So to turn a half into 2, I need to multiply it by 4. And again, we're not just multiplying that by 4, we're multiplying the entire equation by 4. And because I'm going to multiply by 4, I then should also multiply my delta H value by 4 as well. So if we do that, let me rewrite it so we can see it here. We'll go with, that will give me 2 of the N2 plus 12 divided by 2 is 6 H2. Goes to the other side, 4 NH3. And once again, my delta H for this guy going to be my original number. And again, we need to multiply it by 4 because we multiplied the entire equation by 4. So that gives us 46 times 4, it's 184. So that takes care of that. The next thing we might want to look at is we could look at the water, which is also on the left-hand side here, but I do need 6 of them, and I only have 2, so we're going to need to multiply the bottom equation here by 3. Should do that. We will also then multiply our delta H value by 3, and if we do that, that will give me 6 waters, and then that's going to go to the other side, 6 H2s plus 6 O2s. Once again, my delta H here going to be positive 484 times 3. And that gives me 484 times 3, bless you, 1452. Now, clearly I multiplied and did stuff to all these equations. I have nothing left, so hopefully we should be good. So we're now going to add these equations together, and we should end up with the guy on the bottom. So first off, we want to look for anything that will cancel. In this case, 6 H2s on the left and 6 H2s on the right should cancel. And I think that is everything that will cancel, maybe. Let me see here. So I guess I should do proper multiplication, which would mean that would be a 3 when we take 3 times 1. Sorry about that. 3 times 1 would be 3. Now we're good. So that will leave us 2N2 on the left plus 6 H2O on the left. Gives us 4 NH3 plus 3 O2. And that matches the equation that we needed on the bottom. Now for our delta H for this equation, we're simply just going to add our values together. That would give us minus 184 plus 1452. So that is going to give us a value of 1268 for our delta H value. This would be endothermic or exothermic. This will be endothermic, so positive values, so energy overall is being absorbed. Questions on that? So in this case, we did have to multiply, and we want to keep track of what we need to do and how the delta H values change. Any questions on that one there? All right, let's try another one here where maybe we got to flip our equation around or something like that, just to see. Everybody good? Yeah. Let's try this one here. So we're looking to end up with this guy here. And what is the delta H value based on these 3 equations? So in this case, it takes 3. So, okay, let's take a look. So again, best approach just to keep it simple. I see carbon here on the left. I see it in this equation on the left. I need 1 when I'm all said and done. I have 1 in that top equation, which means I don't need to do anything to it. I'm just going to keep it exactly the way it is. So I'm just going to write carbon. I'm not going to write the rest of it. I'm going to leave the states out so don't get too crowded here. Because again, I did not do anything to it. My delta H value will still remain exactly the same. Coming to the next one, we have some sulfur on the left, and we do have sulfur on the left, but we do need 2 of them, which I do not have there. So for this equation, I do need to multiply it by 2, which means I will also then multiply my delta H value by 2. When I do that, I'll end up with 2 sulfurs plus 2 oxygens. Hopefully I'll do better than last time. 2 SO2, that's good. My delta H value here would then be minus 296.1 times 2 kilojoules, again, because I multiplied by 2. Any questions on that so far? That leaves my last one here, which is this CS2, which is on the right-hand side. That is CS2. It's on the left, so I do need to reverse this reaction. I do only need 1 of them, so all I'm going to do is reverse it, which means my reactants become my products become my reactants. So I'm just going to reverse this guy around. And because I reversed it, what happens is this sign will now become positive 1072. So positive 1072 because I reversed it. So I need to reverse that reaction, right? Any questions on that there? Again, at this point, we should be done. So let's see. We have CO2 on the right and left, so they will cancel. We have, in this case, SO2 on the left and SO2 on the right, so they will completely cancel. And in this case, we have 3 O2s on the right, 2 on the left, and 1 more makes 3. So all those guys will cancel. And that is everybody, I hope, at this point. So we got carbon plus 2 sulfurs on the left and CS2 on the right. To figure out our delta H in this case, we're going to add up all of our adjusted values here. So we're going to take minus 393.5 plus 2 times negative 296.1. Again, we need to multiply that by 2 plus positive 1072 in this case. Looks like perhaps 86.3 kilojoules. This case, or in this case, probably to a whole number based on the last one. So positive 86 kilojoules based off of this number and the adding part of it. Yeah. Endothermic reaction here. Again, positive delta H. Question on that. So the best thing to do is just kind of keep it simple, move things the way you will need to move them, keep track of what you did, adjust the delta H values, and then all you have to do is add up all the delta H values. This is again what is known as Hess's Law, a very common way to figure out the delta H of a particular reaction. If you know the delta H's of some individual reactions. Any questions on how to do that there? Yeah. There should be practice problems in the book on this. I think there will be some up on the actual homework too. I think there's some. So there should be some stuff like that. Yeah. Other questions? I think I might have a review sheet up there. I'll also double check, but I'll take a look. All right. So to finish up this chapter here, we've been talking about heat. And again, is that flow of energy due to different temperatures. Delta E is the change in internal energy, and it works the same way. So if you have sort of a negative value for the change in internal energy, that means energy is going to be sort of released, or if it's positive, it's going to be absorbed. The change in energy can be defined as heat, and W is work. So heat plus work will give you that change in energy. A lot of times we use energy to do some type of work, either on a system or against a system. Again, if heat and work is added to a system, is positive, but is removed when it is negative for our delta E. Now, lastly, energy is a driving force. Most processes that occur spontaneously involve an energy spread. A lot of spontaneous reactions are exothermic, but not all spontaneous reactions are really exothermic. There's endothermic ones. A very common example of that is like your ice cube melting, right? If you take an ice cube out, it's going to start to melt, right? You don't really have to do much to it. It's a spontaneous sort of event that will occur. So sometimes people think that all spontaneous reactions that occur has to be exothermic, and they don't. They could be endothermic or they could be exothermic. But exothermic does really help the process. A lot of times it does help it be spontaneous, but there's a lot of reactions that are endothermic. Something that you'll get into in 1B a little bit more is what's known as entropy. Entropy is the amount of disorder there is in the universe. With increasing entropy, it actually becomes more positive. So delta S is entropy, or the change in entropy. And the second law of thermodynamics is that entropy in the universe is always increasing. Places where we do see examples of increasing entropy are all these situations. When you go from solid to liquid, there's a lot more disorder that's happening, right? In the liquid phase, that's a lot more entropy. And as you go from liquid to gas molecules are flying around. So there's a lot more craziness and randomness. And that also increases the disorder. When we make a solution, we're actually dissolving something that breaks these things apart, lets them floating around, causes a lot more entropy. And lastly, if you increase the temperature, things start moving around faster, things have more energy, so there's more randomness, there's more disorder that's happening. That also will increase the entropy. Any questions on that there?